Emergency! Emergency! My soda is exploding! It is a sugary volcano of doom!
Whoa, Ziggy, watch out! You're getting sticky soda everywhere. Wait a second. Did you shake that can before you opened it?
I only shook it 27 times. For very important scientific reasons, I was trying to mix the flavor molecules.
Hoot hoot! It sounds like we have a bubbly disaster on our hands, or wings. But actually, Ziggy, your sticky explosion is perfect timing.
It is? Even though Ziggy is now dripping with grape soda?
Exactly, because today's mystery is all about the science of bubbles, fizz, and foam. Why do some drinks stay flat, while others, like Ziggy's, turn into a volcano?
Please tell me the answer is magic. Is it magic? Or did I just make the bubbles angry?
It isn't magic, Ziggy. It is chemistry. But before we wipe up this mess and dive into the science, let's take a quick break for our show intro. Hoot hoot. Hello, curious minds. You're listening to STEM with Dr. Owl, where big questions turn into fun adventures.
Hi, I'm Emma, always full of questions and ready to explore.
Ziggy here. I know a zillion facts and 0 ways to share cookies.
If you like our show, please share with a friend, a teacher, or your whole class.
Or your neighbor's cat.
Welcome back, junior scientists. We are here with a very sticky robot and a very big question. This topic actually comes from one of our listeners, Ethan from Seattle.
Thanks for the great question, Ethan. We love hearing what you're curious about. Remember, listeners, you can always share your questions with us.
Ethan wants to know why some drinks make lots of bubbles or foam and others don't. To understand that, we first have to meet a very special ingredient called carbon dioxide, or CO2 for short.
CO2? Is that a robot name? Like R2-D2?
Not quite, Ziggy. CO2 is a gas. It's the same gas we breathe out. In fizzy drinks like soda, sparkling water, or beer, this gas is squeezed inside the liquid under very high pressure.
Oh, I think I get it. It's like when you try to pack too many clothes into a suitcase and you have to sit on it to zip it shut.
That is a brilliant analogy, Emma. The gas is squished inside the can, trapped and waiting. But the moment you crack open the tab, the pressure drops and the gas rushes to escape.
Exactly. That fizz sound is the gas escaping. But Dr. Owl, why do the bubbles start at the bottom? Why don't they just disappear instantly?
Excellent observation. Bubbles need a specific place to form. We call these nucleation sites. That is a big word, so let's break it down. Nucleation. Can you say that with me, Emma?
Nucleation. Nucleation.
Perfect. Nucleation sites are like tiny starting lines for a race. They can be microscopic scratches on the glass, tiny specks of dust, or even the surface of a straw. The gas grabs onto these rough spots to form a bubble before floating up.
So if I drink from a dirty glass with lots of dust, I get more bubbles? That sounds delicious.
Well, scientifically, yes, but let's stick to clean glasses. Now, explorers, let's play a quick guessing game I call Bubble or Not. I will name a drink, and you tell me if it bubbles because of trapped gas.
I'm ready. Explorers at home, shout out your answers.
Round 1. Sparkling water. Bubble or not?
Oh, I know. Bubble. It tickles my nose sensors.
Correct. It has CO2 gas. Round 2. Milk.
Usually no. But wait, what about frothed milk? like on a fancy hot chocolate.
That is a great point. Milk can be foamy, but that comes from whipping plain air into it, not from trapped CO2 gas escaping. So bubbles, yes. Fizz, no. Now, round 3, beer.
Bubble, and it has that fluffy white hat on top.
Correct. And that fluffy hat brings us to our next point. Why do some drinks, like beer, have a thick foam that stays for a long time, while soda bubbles pop instantly?
Is it because the beer bubbles are stronger?
Like they work out at the gym?
Oh, not quite. It comes down to bubble glue. Drinks like beer have special proteins and natural sugars inside them. These act like sticky glue that holds the bubbles together, forming a thick foam.
So my grape soda didn't have bubble super glue?
Exactly. Soda is mostly sugar and water. It has no proteins to hold the bubbles together, so they pop very fast. Fizz, then gone.
Okay, but Dr. Owl, we still haven't explained why Ziggy's soda exploded everywhere.
That is because Ziggy shook the can. When you shake it, you mix little pockets of air into the liquid. Remember those nucleation sites we talked about?
The bubble starting lines?
Yes. Shaking creates millions of tiny bubble starting lines all at once. So instead of a few bubbles rising politely, every bubble tries to escape at the exact same second.
So I created a bubble traffic jam? Science made me do it.
Indeed. Now, let's test your bubble brain power with a lightning round of true or false. Question 1. True or false? The bubbles in soda are filled with oxygen.
False. You said it was CO2, carbon dioxide.
Correct. Question 2. True or false? Flat soda means most of the gas has escaped.
True, it tastes like sad, sugary water.
Correct again. Question 3. True or false? Bubbles float down in space.
Ooh, tricky. I'm going to say false?
You were right. In space, there is no gravity to pull the liquid down and push bubbles up. The bubbles just clump together in a weird jelly blob.
Space jelly. I want to go to space immediately.
Hold your rockets, Ziggy. Before we go to space, here are a few fun facts for our explorers. Did you know that if you drop a candy called Mentos into diet soda, the soda will explode into a huge geyser?
Woo! Why does it do that?
It happens because the candy surface has thousands of tiny pits.
Pits? Like tiny holes?
Yes. Each pit is a nucleation site that creates millions of bubbles instantly.
Note to self, do not eat Mentos while drinking soda. My circuits might pop.
Ho ho! One last fun fact. In the very deep ocean, the water pressure is so heavy that bubbles can barely form at all. They get squished.
Wow. So, to recap, bubbles come from carbon dioxide gas trapped under pressure. When we open the can, the pressure drops, and bubbles form on tiny rough spots called nucleation sites.
And shaking it makes a bubble traffic jam, and proteins in beer act like bubble glue. I am now officially the chief bubble investigator.
Hoot hoot! I think you've earned that title, Ziggy. Just maybe stop shaking the cans.
And speaking of bubbles, if you want to try a fun experiment at home that doesn't involve exploding soda, check out our Dancing Raisins activity.
Yes, It is a wonderful way to see nucleation in action. We have posted the steps and instructions on our Instagram page. Ask a grown-up to help you find it.
Thanks for joining us, everyone. And thank you, Ethan, for the great question.
Stay curious, and we will see you next time on STEM with Dr. Owl.
Bye. I'm going to go see if I can carbonate my tomato soup.
Ziggy, no, that's going to be a disaster.
Oh, dear.
Observation log. Tomato soup does not like to be fizzy. It is now tomato rain.
Ziggy, why is the ceiling red?
It is, abstract art. Please do not tell Dr. Owl.
That was so much fun, Dr. Owl. I hope all our explorers had a great time too.
Hoot hoot! We loved having you with us. If you don't want to miss our next adventure, follow us on your favorite podcast platform.
And if you know a friend who loves exploring too, share our podcast with them.
If you have a question or a topic you want to learn more about, leave us a comment. See you next time.